Hi, I'm Mattia Lecci, and I will present you our work on periodic scheduling for mmWave Wi-Fi networks. Communication networks are asked to answer the user demand of increasing capacity with reduced latencies year after year. Applications such as telepresence or extended reality, for example, require gigabit-class connections with only a few milliseconds to reach the receiver. The stringent delay and jitter requirements for these types of traffic streams becomes incompatible with simple networks, and the random channel access of current Wi-Fi technologies is a clear example. When dense deployments and high channel usage is required, stringent constraints cannot be satisfied anymore. Thankfully, the WiGig standards, the common name for Wi-Fi standards operating in the millimeter wave bands, support contention-free channel access periods for persistent and periodic traffic streams. As you can read from our paper, it is not trivial to make streams with different characteristics coexist. So we propose a mathematical framework for defining reliable admission control and scheduling algorithms for WiGig networks. According to the standards, stations can request to the access point periodic reservations. Most importantly, stations can ask for a required periodicity and for a range of duration for each allocation block, going from a minimum required temporal access, also called Tmin, to a preferred required temporal access, also called Tmax. Based on this information and the current status of the network, the access point has to decide whether to reject or not the request. If the request is accepted, it will also have to decide a starting time and the duration of the periodic allocation block. The standards also include some peculiar constraints which make this work largely incompatible with the existing state-of-the-art on resource scheduling. First of all, the standard does not support arbitrary periodicities. Only integer multiple or fractions of the beacon interval durations are supported. Second, allocation blocks cannot be put across two consecutive beacon intervals, only within them. Third, the block duration of the allocated request must fall within the specified range. To make the problem more tractable, we also add some assumptions. Specifically, allocated resources will be maintained indefinitely. Allocation blocks cannot be fractioned into multiple disjoint intervals, and we assume that strict periodicity is required. This means that once allocated, the start time of a request cannot be changed, and thus the start time of any future allocation block is known from the beginning. Instead, we allow the duration of allocated requests to change within the requested interval if needed. The core of the scheduling algorithms that we proposed are based on this feasibility check algorithm, which is mainly needed for admission control of a new allocation. It assumes that the previous n-1 allocations have already been accepted and thus have fixed start times, as follows from the strict periodicity assumption. It then tries to fit the additional allocation, checking for compatibility with pre-existing ones, both in terms of periodicity and block duration. The constraints and assumptions, together with a smart algorithm design, ensure that the stopping criterion is reached in a finite amount of steps. You can see on the left a case where the new allocation is incompatible with the scheduled one. The picture shows every step that the algorithm takes to classify the new request unfeasible, roughly described in the paper together with the pseudo-algorithm. Similarly, the right picture shows a case where the new allocation is feasible. The final step is also able to extract what we call feasible intervals. Feasible intervals simply define ranges of time where the first block of the new allocation can start and finish, by setting the start time and block duration properly, fitting the structure given by the pre-existing allocations. A first scheduler that we proposed is the simplest one based on our framework. It simply chooses the largest feasible interval that can accommodate the new request, or the first large enough to fit its maximum block duration. The algorithm thus follows a first-come, first-served approach. the first requests can take most of the available resources, starving those that arrive later and possibly forcing the admission control algorithm to reject them. The second algorithm that we propose is more flexible, but at the cost of a much more complex design. Details of this can be found in our paper. The goal of this algorithm is to distribute time resources more fairly among all incoming requests, trying also to minimize the rejection rate. Specifically, we define a block duration ratio R for the nth allocation, controlling the block duration between the minimum and the maximum requested times. The algorithm tries to maximize the minimum of these ratios. Once again, the strict periodicity assumption allows us to create an efficient algorithm able to reach the stopping criterion in a finite amount of steps. We analyze the proposed algorithms in isolation, meaning that we do not model the rest of the network, as well as the other layers of the communication stack. Given the specific constraints from the WiGig standards, no comparable state-of-the-art on this topic was found, and thus the algorithms are only compared against each other. To compare and analyze the results, we define the following parameters. Specifically, the interval ratio highlights how flexible the requesting application is, where low values means that the application is extremely flexible, and the ratio equal to 1 translates into a request for an exact amount of temporal resources. Instead, the load factor indicates the fraction of resources that an allocation would request in average. In the first scenario, we only analyze traffic streams sharing the same parameters. They all have a periodicity equal to a third of the beacon interval. Each request requires 10% of the resources in average, and we study some relevant metrics as a function of the flexibility of the request. One of these metrics is James Fairness Index, where a value of 1 indicates that resources have been equally shared among all users, and low values indicate unbalanced allocation of resources. Given the design of the two algorithms, it is clear that the max-min-fair scheduler has a much higher acceptance rate than the simple algorithm. Curiously, when the Tmin is about a half or more than Tmax, the allocations can be considered fairly rigid, as the two algorithms behave similarly. Considering only accepted allocations, the two algorithms show a very high fairness at all interval ratios. Clearly, the increased acceptance rate of the max-min-fair algorithm reflects into a lower average block duration of the accepted requests. And overall, it can be easily seen what the main characteristics of the two algorithms are. The simple algorithm focuses on a high resource allocation for few requests, whereas the max-min-fair algorithm favors high acceptance rate, sacrificing the amount of resources given to each single request. In the second scenario, instead, we wanted to focus on the main motivation of this work, meaning the coexistence between inhomogeneous applications. We create requests for two types of traffic streams with different periodicities, while keeping a constant load factor and interval ratio for both types. To analyze whether allocations of different types can coexist, we define the variability as shown. Note that a value of 0 means that only requests of a single type were accepted, whereas a value of 1 means that requests of type C1 and C2 were accepted in equal numbers. From these first two figures, it is possible to notice the strong biasing effect of the first accepted request type. In fact, especially the simple algorithm, once the first allocation is scheduled, it will be harder for subsequent allocations with a different period to fit the constrained beacon interval, making the scheduler favor allocation with the same period. This figure further confirms the previous analysis, showing again that the simple algorithm favors more homogeneous beacon interval allocations. The max-min-fair algorithm instead is able not only to accept many more allocations, but it is also able to accept a wider and fairer variety of allocations. This, though, comes at a cost. In fact, accepting large quantities of allocations of different types almost surely brings the beacon interval to be left with some unfillable holes. The gravity of this will depend on the type, variety, and distribution of allocations, although in our tests we always found high beacon interval occupancies. To conclude, in this paper we proposed a mathematical framework to analyze and design scheduling algorithms for WGIG systems, together with 2 examples. The first algorithm is quite simple, resulting in few allocations to be accepted and with low allocation variability, but with high beacon interval occupancy and block duration. The second algorithm instead results in high acceptance rate, allocation variability, and fairness in general, at the cost of a much more complex design and reduced block durations. This paper should also make a careful reader appreciate the difficulty of designing this type of schedulers. This paper opens the possibility to further study the problem in different directions. Our work will focus on the implementation of these algorithms on a full-stack simulator, analyzing the behavior of the full communication stack at once. Another possibility is to further extend this mathematical framework, for example by relaxing some of our assumptions. Allocating multiple users at once, exploiting the directionality of the mmWave channel, could greatly improve the sum capacity of an access point, while studying the impact of realistic non-stationary channels could give a more practical point of view on this work. Finally, real applications might not be perfectly periodic. Further studies should focus on how a real application could benefit of periodic scheduling and which pitfalls might be encountered on the way. Thank you all for your interest. Please feel free to contact us for any further clarification.